I can shout. So it's a great pleasure to come back to Amplitude. It's been a while. So I'm going to today I'm going to talk about this mixing of DGLAP and BFKL detectors. What is done with these excellent collaborators, Xianhuang Chan, HuaXing, and David Simon's company. But to begin the talk, I need to explain what I mean by DGLAP and BFKL detectors. So that would be the first thing I want to talk about. And these detectors, even before that, we saw a very nice talk on Monday. The Reggie trajectory in QCD. These are the really the signature of particle physics, because we see these beautiful resonances in the scan of energy, and you can align them in a very beautiful straight line. There's a talk by Andre on Monday. It's happening at low energy. By low energy, I mean it's below a few GeV. But nowadays, we also have the access to the UV limit of QCD. At the LHC, we can collide protons at 7.5 GeV energy. And these protons, after collision, they produce a large number of particles. So in this limit, discussing about the individual spectrum of these particles doesn't make too much sense, because the energy is so high that all the particles is essentially becoming massless. So one way to study this high energy collision is not, again, and also the number of particles is also very high. Computing the scattering amplitudes for the production of 100 or 1,000 particles is beyond the reach of current technology. One way to do that is, instead of expanding in the number of particles, we can expand in the number of detectors. So these detectors, they record the energy of the particles flowing in particular directions. You can insert one detector, two detectors, and more detectors. And these detectors, they actually probe another type of Reggie trajectory in our theory, which is in QCD. In the case of QCD, is the perturbative DGLAP and BFKL trajectories, which is the center topic of my talk. And in some sense, there is a connection between these two types of trajectory in the case of ADS-CFT duality, because we know that the operator, these trajectories are formed by local operators in the field theory, and these operators, if they are in the case of a CFT, they have a dual in the ADS case, then the dimension of this operator actually can be considered as the mass of the particle in the ADS space. So there is an actual intuitive connection between these two pictures. But for QCD, for real QCD, we know that this connection is doesn't make immediate sense, and we know there's this confinement barrier between the UV physics and IR physics. And to connect these two pictures actually is one of the dream of quantum field theory, I think. But then let me start from the what is a detector in experiment. In the experiment, when we do the collision, we have particles coming out of the collision, and we have different slices of detectors that recording its energy depositions. Traditionally, experimentalists like to think about particles in this momentum space to diagonalize translation. But actually, there's another way to better way to think about it, which is by diagonalized boost. We can do a mirroring transform. For experimentalists, what mirroring transform means is that they take different events and they look at a particular angular directions, and they weighted the events by the energy that goes into that particular directions. The energy could be raised to a certain power, and then sum over all the scattering events. That would, in that way, they could perform a mirroring transform to the scattering process. On the theory side, we can also describe what they do, which is very straightforward. It's just you have a operator that counts the number of particles that go in a particular direction, and then you reweight that phase space integral in that directions. this can be written down in free theory. You can also turn it into an operator form that could possibly include interactions. One way to do that is to perform this light transform. If you have a local operators with an even spin, then in the free limit, in the free theory limit, if you actually reduce to this particular form for given spin and dimension, and this particular transform would give rise to a operators that actually lives on the future now infinity. It's an integration on this future now infinity, and it also plays the role of turning the local dimension and spin to the Lorentzian dimension and spin. And this transformation will actually swap the spin and dimension in this particular way. And this is a very important fact that I will talk about this Lorentzian dimension and Lorentzian spin in the rest of my talk. Now for local operator or twist operator, this is actually has been studied since the very early days of QCD. So you can write down their locally. You can write down their operator form, and they will sit on a spin, let's say spin 2, spin 4, and spin 6, etc. And in QCD, we actually know a lot about this operator. Actually, there's ongoing efforts to compute the enormous dimension, which is measuring the horizontal shift from its free theory limit. There's ongoing efforts to compute this enormous dimension at 4 loops order. And they also have, the reason is that they have very important phenomenological implication use, because they are really telling us how the parton distribution functions are evolved under the energy scale, under scale Q. There's also another trajectory, which is so-called the BFKL trajectory. It's also has been studied since the very early days of QCD, and it plays a perpendicular role in this figure, which tells you how the number of particles grows when the momentum fraction of the particle carry reduced. And furthermore, this operator, they are actually, and by the way, there's a third. By the way, this operator actually it doesn't sitting there isolated as a single point. They actually connected it to become a trajectory. So we call it the DGLAP trajectory and this the BFKL trajectory. And you notice that Lipatov play very important role here because its name show up here and here. But I would also like to point out that Parisi also plays an important role here, because there's a third trajectory which is so-called the shadow trajectory, and the shadow formalism in CFT is developed by Parisi and his collaborators in early 70s. Okay, so these are the few of the very beautiful plots for how we can understand these trajectories in a theory that is can be calculated analytically or to all orders. So people has been studying this trajectory, how they deform when you turn on the interaction in the case of n equals 4 super-Yang-Mills theory using the ADS CFT duality, or using the integrability methods, or again using the integrability methods, but for the higher twist trajectory. You can see it could become very complicated when you go to higher twist. There's many operators here. How to connecting them is not a non-trivial thing to do. But we will be focused on the trajectory in QCD, and in particular in a perturbative limit. So there are 2 ways in QCD to probe this trajectory experimentally. The first way is that we take the simplest operator in this trajectory, which is the average now energy operators, which is the light transform of the stress tensor, the red point here. Sorry, the arrow is yeah, the arrow is right. Sorry, it's the black dot here. We can take many of these detectors are very nice. They are protected detectors, which means that they don't receive quantum corrections. we can take many of these detectors and consider their correlation functions. In that way, we can probe other points in this trajectory. For example, if you take two of these ANAC operators, you could produce a third operator sitting here at spin j equals 3, which actually doesn't have a local operator correspondence, but it is there in the in your theory. There's a second approach. This is not the main focus of my talk, but I have to I can't resist telling you that there's a lot of experimental progress by thinking about physics in this way. Now there are many different experiments being carried out to measure the scaling behavior when the angle of these two detectors become very close to each other, and using that information you can extract very detailed information about the standard model and also the QCD itself. So this is one approach, and the second approach, which is the focus of my talk, is that we can directly, as I told you before, when experimentalists do the Melling transform, they are weighting their energy in particular detectors by JL, by some related JL. So from the experimental point of view, this is a free parameter to them. They can dial these parameters. So you can, in other words, we can move this. In other words, if we start from somewhere here, we can horizontally move in these plots to find some place that's interesting to study experimentally. And I think everyone can appreciate that one place to look for is in this intersection. Experimentalists should actually dial JL to -2 to see what would happen at the intersection of DGLAP and BFKL. And then if you look back into what the operator is defined in that particular point, it's defined as weighting by 1 for each of the particles in that particular direction, which means that it's counting the operator sitting there, is counting the particles flowing to the particular direction and there. So it count, yeah, it actually it's counting the partons that flowing in that particular directions. So this, of course, is a very important question in QCD, and it has been asked a long time ago, and people found the answer to that question. They found that this counting the multiplicity can be actually resummed to orders in perturbation theory by summing a set of ladder diagrams. And the results that they find at that time, I think would be is surprising, is that they find the results is proportional to the square root of alpha s. So it's not something that you will see in a single in a finite order of expansion in perturbation theory. It's a well-known result in QCD, but what I'm going to tell you today is a new way to understand these results. So what we want to understand is that what experimentalists do is counting the hadrons in some particular directions. These hadron detectors, they are highly non-perturbed. We don't know how to compute their correlation function, but we could try to do a operator product expansion. These are the operator. The N are the operator living in the IR. We can do a operator product expansion to the UV operator, which is the perturbative detector that we can try to calculate. And the matching coefficient will be non-perturbative. It's so-called the fragmentation or moment of fragmentation function. But this operator matrix element will be perturbative. In the transitional QCD language, it's the Wilson coefficient. Then the Q evolution of the hadron multiplicity will be determined by the dimension, enormous dimension of our perturbative detector operators. So once we understand what the perturbative detector operator, what is the dimension of the perturbative detectors, then we could predict the hadron multiplicity evolution. That's the goal. And we know that, and before we actually do the calculation in quantum field theory, we know that something interesting happened, even in terms of quantum mechanics. If you have a Hamiltonian that exists some small parameter, let's say W, the off-diagonal perturbation, if you turn off the this off-diagonal perturbation, the two energy will collide. The two energy level will collide with each other at some point. But once you turn on the interaction, you actually they will split away. But the splitting will not be obvious in the perturbation theory. If you expand this energy eigenvalue in perturbation theory, which the small parameter is W, you will see divergences at each order in perturbation theory. But once you sum up everything, you get a finite result. So this is a very simple example that you can simply. So in other words, there's two ways to actually separate this trajectory. The one way is to sum this series in perturbation theory, which is what in QCD people do in 80s. The other way is actually find the energy eigenstate and try to diagonalize your Hamiltonian, and then you will also get your eigenvalue. So that's the way that we are trying to do here. And the strategy is the following. First, we will try to calculate the matrix. So we have this DGLAP operator, which is kind of we understood what they looks like, and we can calculate their operator, the matrix element for them at one loop level. And then we would expect to find some divergences, and the divergences will happen at the intersection point. That intersection point is dictated by the value of JL, which is -2. So we would expect to find a pole at JL equals -2. And then we will try to identify the origin of this pole in our calculations. Once we identify the origin, we can try to construct a new operator, the BFKL detector, that could give rise to this pole. And once we constructed this detector, we will be able to diagonalize the Hamiltonian and get the results we need. So this approach has been done for the Wilson-Fisher theory and also recently for the critical ON model. Okay. Now let me start from the DGLAP detectors. As I told you, the DGLAP detector is a light transform of a local twist-2 operators in QCD. If in the free theory limit, it's very simple. It's just counting the number of particles in a particular directions. And what we need to do is to calculate the matrix element for these particular operators. We can choose we can choose the simplest state we can create, which is let's say a scalar source or a electromagnetic current. So we can use this, or in the amplitude language, these are the form factor. We insert this operator inside the form factor squares and perform this particular phase space integral for that detectors. So you see that the detector actually is integral with some weighting parameters JL for the energy for the energy of the particle going in some particular directions. This is actually a very straightforward calculation, so there's no need to explain the detail. But the result is the following. And as I told you, you see explicitly from the results that there's a pole in JL equals -2. This is the leading pole in the JL axis. And you can, this is the result by doing a one loop calculation. So you need a real emission and also a virtual emissions. But what I want to explain that what is the origin of this pole. So the origin of this pole actually is coming from the phase space integral of a soft particle. So this is if JL exactly equals -2, then this is the standard phase space measure for a particle. But now because we have this JL as a parameter, we can control it, we can move it slightly away from JL. We have analytic control of that, so it regularizes the poles there. So which tells us that the origin of this JL pole and then also the origin of that mixing with the BFKL detector is coming from the soft radiation. For soft radiation, of course, this has been studied for many decades, and we know very well the soft radiation in gauge theory. For example, if you radiate a soft quark, a soft gluon at the square amplitude level, you can write the square amplitude as the soft factor, which is of course also very well known, and the amplitude that with the soft gluon strip off, and but also with some color density matrix in between. So because the gluon carry color, the square will have a mismatch in color, which I would denoted by TAJ here, the color emitted in the J, in the line J. So that tells us how to construct, because this is the origin of the mixing, that tells us how to construct the BFKL detector to remove that mixing. And the idea is that this particular soft factor can be written in this operator form. You can have two number detectors or the color detectors. We can have two color detectors which measure the color going out from that particular line, and a soft factor, and then we integrate it over. And because we are interested in the probability of radiating a soft gluon, the direction of those two color detectors doesn't matter. So we integrated out their direction dependence, and that gives us the probability of producing a soft gluon at a particular direction Z. You can also understand this from the Lorentz symmetry. This prefactor is the kernel that make the symmetry counting work on both sides of formula. But once you write down the operator, calculating its matrix element becomes straightforward. For example, at the Born level, so this is a trivial order, you only have two particles. Let's consider a form factor with the two gluon. At tree level, you only have two detectors, but there's no soft radiation. At one loop, you could have one soft radiation and a virtual loops. And in both cases, you integrate it over the direction of your color detectors, and also with a prefactor, which is dictated by symmetry. And that's what you need to calculate the matrix element for the BFKL detector. And the results after calculating those matrix element, the results, I can summarize the result in this approach. First of all, we know that these two detectors, they actually coincide at a particular point, which is JL equals 2 minus D in D dimension, if you are using dimensional regularizations. And what we see, and then when you calculate the matrix element for the DGLAP, you would find 1 over epsilon pole. That's the normal twist-to enormous dimension for DGLAP trajectory. You will also find a pole in JL equals minus 2. That is telling you the fact that this operator will mix with the BFKL detector at this particular value of JL. And you will also find a UV, a epsilon pole in the BFKL detector matrix element, which will directly give these UV poles, will give you directly the BFKL eigenvalue. So this actually is a new way to directly compute the BFKL eigenvalue directly. And finally, you will also find a pole at JL equals 6 minus 2D, which is telling you that this BFKL will again mix to the, this BFKL detector will also mix into the DGLAP detector. Once you know this, the structure of this mixing matrix, you can construct a basis that try to remove the degeneracy at the red point. And also you can try to remove some of the poles in JL equals 2 minus D. And in that new basis, you can diagonalize your Hamiltonian. And after diagonalization, what you get is that these two trajectories no longer intersect with each other, and they have some separation at JL equals minus 2. In particular, the separation at this particular value is proportional to a square root of alpha S, which is a result that found many years ago used by resumming all the Feynman diagrams. But here we are not doing resummation. We are just diagonalize the matrix. And this actually suggests that you can try to measure this trajectory. As I told you, experimentalists can just dial this parameter JL to scan over the horizontal axis. And we do a PCR simulation using both quarks and gluon sources. And I told you that the longitudinal, the vertical axis measure how the observable scale with energy. So you can extract that exponent, and with that you will get a curve like this. The free theory line is on these two, but the actual simulated data looks very similar to something you see in N equals 4 Silver-Yang-Mills theorem. Okay, so to briefly summarize, we see that there are DGLAP detector in experiment. You could also possibly probe BFKL detector in experiment, and they are actually connect together through the leading soft theorem at a particular intersection of this trajectory. And then you see the connection between intersection and this soft theorem. There's another intersection here, which is the intersection of the DGLAP trajectory and the shadow trajectory. And what would that intersection tell us about? Well, it will tell us about that there should be a pole at JL equals -1. What is a pole at JL equals -1? That is a subleading soft divergence in your matrix element. In other words, to briefly summarize, this shadow symmetry tells you that the existence of a JL equals -1 pole, which is a soft theorem in your square matrix element square. And that shadow trajectory is dictated by symmetry. It's not imposed by hand. It's really, so in other words, there is a shadow symmetry that tells you the existence of subleading soft theorem. So then once you understand this, you can actually simultaneously demixing all three trajectory, and that's what you will get once you do that. But that comes to my conclusion. What I want to tell you is that it is an advantage to think about QCD in the language of detector, because heteronization is invariant under Lorentz boost, which try to diagonalize that action. And also singularity in twist 2 enormous dimension is a signal of intersection between trajectories, and that also tells you that the leading soft theorem can tell you about how to demix these two trajectories, and the existence of shadow trajectory tells you about the subleading soft theorem. And then resumming, then you can do the resummation by just diagonalize these two trajectories. And finally, it seems that it provides a new way to calculate the BFKL eigenvalue directly. And there are also, but there are many open questions I think we need to understand in the future. Maybe I will just stop here. Thank you very much.